Hello and welcome to another ramble with your clumsy maths teacher here. We are busy with the department's grade 12 maths paper 1 from May 2023, and today we're looking at question 8. Right, let's get into it. So we are given a function, a cubic function, f of x is equal to x cubed plus 4x squared minus 7x minus 10. Okay, and then the first few questions are pretty standard, I think. Write down the y-intercept of f. So remember, y-intercept is where x is equal to 0, right? So if we have our Cartesian plane and we have our cubic graph doing something like that, who knows? That is our y-intercept, and the y-intercept occurs when x is equal to 0. So we need to figure out what the y-coordinate is. So we are going to say, okay, what is the value of the function when x is equal to 0? So that would be 0 cubed plus 4 times 0 squared minus 7 times 0 minus 10. And as we can see, this term is going to disappear, this one disappears, and this one disappears as well. So all we're left with is negative 10. So that means the y-intercept occurs at the point 0 and negative 10. Okay, so my sketch is definitely very off. Our graph is actually going to cut the y-axis somewhere down here. Anyway, okay, so that's our first question done and dusted. Right, so let's just put that. Y-intercept occurs over here. Right, next question says, show that 2 is a root of the equation f of x is equal to 0. Right, so in other words, if we substitute 2 everywhere where we see an x, does this expression end up equaling 0? So we're going to determine, okay, what is the value of the function when x is equal to 2? And that is 2 cubed plus 4 times 2 squared minus 7 times 2 minus 10. I hope I still have my calculator. Yes, I do. All right, so let's just put that in. Right, and we get 0. So therefore 2 is a root or a solution. Right, let's write that in the English that we know and love. So 2 is, and let's be more specific, x equal to 2 is a solution to the equation f of x is equal to 0, so it's one of possibly many x values that make that function output a value of 0. So we have proven that, right? And then the next question says, hence factorize f of x completely. Okay, so what we know, what that previous question has allowed us to do is to say, okay, we know that when x is equal to 2, this expression over here is equal to 0. So in other words, this expression, x cubed plus 4x squared minus 7x minus 10, okay, we know that that is equal to 0 when x is equal to 2. And another way that we can express it is we can express it in factorized form as x minus 2 times some other expression is equal to 0, right? We know that it factorizes this way because in order for this to be true, one of the solutions would be a solution where x minus 2 is equal to 0, therefore x is equal to 2, right? So we're kind of reverse engineering this thing, right? What we also know is that this expression over here in the brackets is actually, let's do another color. Let's make it orange, right? So we know that this expression here is a quadratic expression. Okay, and so now we can kind of expand it so that, yeah, okay, I'll explain as we go. So we've got x times ax squared. So that is going to be ax cubed, right? And in fact, we already know that the a is equal to 1. But anyway, for the sake of completeness, let's just go with it. Then we've got x times that, which is going to be bx squared. And then we've got x times this, which is going to be cx. Then we have negative 2 times that, which will give us negative 2ax squared. And then we have negative 2 times that, which will give us minus 2bx. And then we've got that, which will give us minus 2c. And we are told, okay, well, we're looking for, yeah, the places where it's equal to 0. Well, yeah, we don't actually really care about the 0. We just want to factorize it, really. Okay, but anyway, let's just go with it for now. So this is b minus 2a if we write x squared. And over here we've got c minus 2b times x, right? And then we've got minus 2c is equal to 0, right? So if you multiply this out, you get this, and with that you get this. If you multiply x with c, you get this, and if you multiply it with negative 2b, you get this term. So that's what's going on there. Okie dokie. Right. So, like I said, we don't actually really care about the equal to 0. All right. What we care about is factorizing this thing. So, actually, what we can deduce is, okay, ax cubed is equal to x cubed, right? We know that b minus 2a x squared is equal to 4x squared, right, from this original expression. We know that c minus 2bx is equal to minus 7x. And then lastly, minus 2c is equal to minus 10, right? So we can use these equations to figure out what a, b, and c are. Okay, so easiest one is a is equal to 1, right? We can see that straight away. Okay, the invisible one over there. And c must be equal to 5, because negative 2 times 5 is equal to negative 10. And then we can use either of these to figure out what b is. So let's use one of them. So we know that b minus 2a is equal to 4. We know that a is, a is 1, right? So b is going to be equal to 4 plus 2, which is 6. And we can just double check by putting it in here. So c is 5 and b is 6, we think. And that is going to be equal to 5 minus 12, which is negative 7, which is indeed what we have over there. So we have a bit of confidence in our answer. Right. Ooh. Right. Okay, so let us shrink some things. Okay, so now let us use the information that we just found to finish factorizing our expression, right? So we have figured out now that x cubed plus 4x squared minus 7x minus 10 is in fact the same as x minus 2. And then over here we have x squared plus 6x plus 5, right? Because we found what the coefficients for the quadratic factor are. So now we need to figure out, okay, can we factorize that quadratic expression? And indeed we can. It's a nice straightforward one. X plus 5 times x plus 1. And so just like that, we have managed to factorize our cubic expression. Righty-doos. So, and that's what they asked for here, hence factorize it completely. Okay, right, so let's just write down what we now know. We know that our expression f of x, our function, is the same as x minus 2 times x plus 5 times x plus 1. And we also know that we have the y-intercept at 0 and negative 10. Right, so it is further given that the coordinates of the turning points are approximately at 0, 7, negative 12,6, and negative 3, 4, 20,8. Draw a sketch graph of f and label all intercepts and turning points. Okay, great. So I'm just going to be super pedantic and draw some axes for us. Okay, oops. There we go. Right, so that being our origin. Okay, and we know that our y-intercept is somewhere down here, right, at 0 and negative 10. Okay, we can also see what our x-intercepts are, right, because remember x-intercepts occur where the graph outputs 0. So in order to figure out where that happens, we've got our factors here that tell us when x is equal to 2, or when x is equal to negative 5, or when x is equal to negative 1, right? We're looking for the values of x that will make any of these brackets equal 0, because then the whole expression will equal 0. Right, so we know that we've got an x-axis, an x-intercept here. We have another one at negative 5 and 0. And then the last one is at 2 and 0. Okay, right, then we're also told that our turning points happen at 0, 7 and negative 12,6. Okay, don't know why this thing is so far down. Now I'm just gonna be lazy nyana and extend my thing without a ruler. Okay, right, so one of our turning points is down here. 0, 7 and negative 12,6, and then negative 3, 4 and 20,8. So I think we need to move some things. Okay, right, so negative 3, 4 and 20,8, so maybe somewhere up here. Negative 3, 4 and 20,8. Oh, I also don't label my axes. Bad. Right, okay, so that means our curve looks something like this. Oh, watch me miss all my points. Right, something like that. Of course, you will try to draw a graph that does go through all the points you plotted. But yeah, there we go. This also just coincides with our intuition, right? Because remember, if you have a cubic graph and the coefficient of x cubed is positive, then we're going to have a graph that goes like this. But if the coefficient of x cubed is negative, then it will be a graph that goes like that. So because our x cubed in this case had a positive coefficient, it makes sense that we have a graph that's going right. Okay, so that's our graph, and we've labeled everything, right? We've labeled our intercepts and our turning points, so that's good. Righties, last question, last part of the question. Use your graph to determine, okay, we're going to need our graph. I think what I'll do is I'll just duplicate this page. Then I'm going to take this question. Oops. I'm not sure where to put it yet, so let's just minimize that for 2 seconds. Then I'm going to clean up a bit. Okay, I think this graph can also afford to be shrunken. If it can be shrunken, that would be great. It took away my stuff. Shame on it. Okay, so we just need to write down what that said again. So this turning point, I think, was at -3,4 and 20,8. Okay, right. So now let's see if we can shrink our graph. Actually. Okay, then lastly, let's move this guy up. Okay, righty. So use your graph to determine the values of x for which f prime x is negative. Okay, so we have to think about, well, what is f prime? What does f prime represent? F prime tells us about the gradient of f. So if we're looking for places where f prime is negative, we are effectively looking for places where the gradient of f is negative. And what does negative gradient look like? It looks like this. Right? So we're looking for what are the parts of our f graph where the gradient is negative. So we see that in this part of the graph, we have a very positive gradient, then we hit a turning point, then it goes negative, and then we hit another turning point, and then up we go, positive gradient again. Right, so effectively, the place where we are getting a negative gradient is here, this part of the graph, right? And which x values produce that part of the graph? Well, it starts here, okay, and then it ends here, right? And the first here is at -3,4, right? When x is greater than -3,4, and then it stops here, right? When x is at 0,7. So as long as x is between -3,4 and positive 0,7, right, the gradient of the graph is negative. Why do we not include 3,4 and 0,7? It's because at those points the gradient is 0, right? And we're looking specifically for places where the gradient is smaller than 0. So be careful about, just think carefully about whether to include your bounds or not. Okay, is this doing anything, or am I just kidding myself? Right. Oh, I took away my answer. Okay, anyway, the answer for the first one is x must be between negative 3, 4 and 0, 7. Right. The next question says we need to figure out the values of x for which the gradient of a tangent to f will be a minimum. The gradient of a tangent to f will be a minimum, the smallest it could possibly be. So obviously it's going to be somewhere again between negative 3, 4 and 0, 7, because the gradient of the graph is negative here. So the gradient of a tangent to the graph will also be negative. And negative numbers are small numbers, we have to remember that. Okay, but we need to figure out where exactly that minimum occurs. So let's look at the expression for f prime, right? So f prime x, well, okay, first let's remind ourselves what is the function to begin with. So that is f of x is equal to x cubed, and then I forgot the rest. It's x cubed plus 4x squared, okay, minus 7x minus 10. Okay, x cubed plus 4x squared minus 7x minus 10, right? So f prime will then be 3x squared plus 8x minus 7. And we are looking for the place where this graph, well, this function produces the smallest output, the smallest y value. So if we were to visualize the graph of f prime x, right, it's a parabola, and yeah, I'm not really sure how to sketch it, but at the very least I know that it's a concave up parabola, right? And we can see, okay, when the x values are here, we're getting what do I try to say? Oh, guys, my brain is not even functional. Okay, essentially what we're looking for is, okay, let me just label this. So this is the value of f prime, and these are the x values, right? We're looking for the x value that gives us this f prime value, right? Because this x value is giving us the smallest possible f prime, right? So then we know that, okay, f prime is its smallest at this x, which means that is where the tangent will be at its smallest gradient, right? So how do we find the minimum for a parabola? There's a couple of ways we can do that. So we could either differentiate this and then equate it to 0, okay, because you're finding the gradient of the gradient. So that's the one way. Otherwise, we can do it, we know that for a parabola, the x-coordinate of the turning point is given by minus b over 2a, right? If we're talking about a function that looks like this, right? So I think that's the quickest, actually. So we can then find this turning point over here by subbing in b is equal to 8, a is equal to 3, so that gives us negative 4 over 3, right? So yeah, this x value is negative 4 over 3. That's where this expression is its smallest, the smallest it can possibly be. And then going back to the original context, what that tells us is that the gradient of f is at its smallest when x is equal to negative 4 over 3, or negative 1 1/3, so maybe somewhere here, right? That's where the gradient is the smallest it can possibly be. So what are we asked? Where will the gradient of a tangent to f be a minimum? It will be when x is equal to negative 4 over 3. All right. I don't know how easy that is to find on the graph, but anyway, maybe there's something I'm missing. Okay, let's just quickly shrink things. Okay, right. So last question says the values of x for which f prime x times f double prime x is smaller than or equal to 0. Okay, right. Interesting things happening. So we're looking for the places where the values of f prime x times the values of f double prime x are going to be smaller than or equal to 0. Okay, so let's talk about, okay, we already know that f prime tells us about gradient. Okay, f double prime tells us about concavity, right? So when f double prime is positive, then we know that our graph is concave up, and when it's negative, our graph is concave down. So very roughly, okay, we have two things going on here. So we have f prime is positive over here, and then again over here, all right? And then f prime is negative for these values of x, okay? And then it's equal to 0 over there. Okay, so that's the one thing that's going on. Then the second thing that's going on is f double prime is concave down. Let's do this with a highlighter rather. So f double prime is concave down, maybe up to there somewhere, right? And then after that, it's concave up. Okay, so if we were to take an x value over here, right, that would be f prime is positive at that point, right, because the graph has a positive gradient at that point, and f double prime would also be positive at that point, because at that point the graph is still concave up. So if you were to times them together, then you would end up with a value that is bigger than 0, that is positive. So a point like this one doesn't fall into the x values that we're interested in, because we're looking for places where f prime times f double prime are smaller than or equal to 0. Okay, so we're just getting a feel for things before we get into the nitty-gritties, right? So that point wouldn't work. Wait, I actually want those zeros. Okay, right, let's look at another point. Let's look at this point, this turning point. So we know that at that point, f prime is equal to 0, right? Because it's a turning point. What's happening with the concavity? The concavity is still concave. Oops, I lied about the previous point. I lied. Okay, let's talk about that previous point again. Okay, so we said for this point over here, okay, the gradient of the graph is positive, good. The concavity is negative because our graph is concave down, okay, at that point. So actually this point is part of the x values we're interested in, because at that point, if we times f prime and f double prime, we do end up with something negative. So our x values have to include this point, for example. Okay, right, now let's go back to what I was busy with, which is this point, the turning point. So we know that at that point, f prime is 0. The graph is still concave down, so f double prime is negative. And if we times them together, we're going to end up with 0, right? Because of this guy. Okay, so that point, for example, also has an x value that we're interested in because it satisfies this condition, right? Let's look at maybe 2 more points. Oops. Ooh, what did I get rid of? Yeah, I'm just destroying more and more. Okay, you know what, I give up. Okay, so let's look at another point. Let's look at this point over here and what's going on, right? So at that point, f prime is negative. The gradient is negative, right? And f double prime is possibly concave. So we're possibly looking at a part of the graph where it's concave up. So f double prime would be a positive number. So then f prime times f double prime at that point would be smaller than 0 because because the one is negative, the other one is positive. Okay, let's look at one more example. Let's look at a point over here and see what's going on. So at that point, f prime is positive gradient, and the concavity is concave up, so that's also positive. So if we times them together, we're going to end up with a positive number. So a point like this should not be included in our answer, right? When x is somewhere here bigger than 2, we can see that this condition will not be met, right? Because f prime times f double prime will actually be positive, not negative. Okay, so now that we've gotten a feel for what's going on, let's try to formalize what we're saying. Okay, so in order for f prime times f double prime to be smaller than or equal to 0, okay, we need, okay, I'm just going to experiment with writing it a certain way. I don't know if it's going to work out. Let's see. So, oops. We need f prime, f double prime, okay. We either need f prime to be positive and f double prime to be negative, or f prime to be negative and f double prime positive, or f prime to be 0 and then we don't care about what f prime is doing, right? So at our turning points, or this can be anything, but f double prime must be 0, i.e. a point of inflection. Okay, right. So those are the 4 cases that we want. Okay, we want to see for which values of x is f prime positive and f double prime negative. In other words, for which values of x is the gradient positive and the concavity of the graph is concave down, or vice versa, and so on. Okay, so I'm just going to have that as a side thing somewhere in some corner. Okay, so we already know that f prime is, okay, no, what am I saying? So we already kind of know where f prime is positive and where it's negative. We know that when x is smaller than negative 3,4, right, f prime, the gradient, is positive, right? So that's this part of the graph. Okay, or let's just stick with how I've been writing it. So it's positive, right? And then when x is equal to negative 3,4, then we know that f prime is 0 because that's where the turning point is. And then from there, as long as it's smaller than 0,7, our gradient is negative. Okay, wait. Trying to shrink things again. Okay, and then when x is equal to 0,7, we have another turning point, right? So the gradient is 0. And then finally, when x is greater than 0,7, our gradient is positive again, right? So the turning points are what are kind of our breaking points, right? Where we go from positive to negative gradient and from negative gradient to positive gradient. Okay, so we have those values for our f prime. For f double prime, we're going to need to differentiate first. So f double prime, okay, we're going to differentiate this guy, so that will be 6x plus 8, okay, and 6x plus 8, right, if we were to draw a graph of that for ourselves, we know that that's a straight line, y-intercept at 8, positive gradient, right, and this x-intercept over here is happens when this function gives us 0, so 6x is equal to negative 8, x is equal to negative 4 over 3. Oh, interesting. We bumped into that number not so long ago, didn't we? Right, okay. So what this is telling us is that when x is smaller than negative 4 over 3, f double prime is negative. And when x is bigger than negative 4 over 3, f double prime is positive. Right. And then obviously at x is equal to negative 4 over 3, f double prime is equal to 0. Right. Okay. Whew, it's getting hot in here. So hot. So let's shrink things as we mull. I mulleth. Okay, so now what we can do is we can, okay, so I'm also just going to do another thing that is going to make my life a bit easier, right? I just want to emphasize that this is negative 1 comma 3 3 3 and so on, right? So if we extend, okay, first let me write the table for f double prime. So the f double prime one is very straightforward. We're just looking at the case when x is smaller than negative 1 comma 3 3 blah blah blah, when it's equal to negative 1 comma 3 3 blah blah blah, and when it's greater than negative, battery dying, 1 comma 3 3 blah blah blah, right? And we've seen the behavior of f double prime. So when x is less than negative 4 comma 3, we said that our f double prime is negative, and then when it's equal to that it's 0, and then when it's greater than negative 1 comma 3 3, then we end up with a positive f double prime. So now what we want to do is we want to, I think it might be easier to work with this on the actual graph. So what I'm going to do is I'm going to redraw this graph and just make things clean. Okay, it's actually good that that didn't work out, because now I can preserve the axes and not have to redraw them. Okay, so our graph looks something like this. Okay, right. I wish I'd drawn that in a different color, but anyway. And we know that, okay, over here, this is x is equal to negative 3 comma 4. Over here, this is x is equal to 0 comma 7. Okay, and then we also know that, okay, so let's just do one thing at a time. So we know that f prime is positive here, okay, and also over here, right? And then we know that it is negative over here. Okay, so that's the first thing we know. Then we also just found out that our point of inflection happens when x is equal to negative 1, 3. So let's say somewhere over here, x equal to negative 1, 3, 3, blah, blah, blah. Right, that's where we are changing from concave down to concave up. So let's just highlight that for ourselves. So it is concave down over here. Okay. And then it is concave up over here. Right. And so what we are interested in, okay, the first case that we are interested in is the case where f prime is positive, okay, and that is the lime green part of the graph, and where f double prime is negative, so where our graph is concave down, so that is the pink part of the graph. Oops. Yes. Okay, so where is that? That is over here, right? We can see that our graph is concave down, the gradient is positive, and then where does that change? It changes over here at the turning point, because after that, we're now no longer in the green part of the graph, we're in the gray part of the graph, where the gradient is negative and the graph is concave down, so you would have a negative times a negative, so that's not what we're interested in. So it's just that first part that we're interested in. In other words, when x is anything from negative infinity up until here, right, which is where x is equal to negative 3, 4. Okay, and then always ask yourself, are we including the boundary or not, right? And so in this case, we do include it because remember, we're also interested in the places where f prime is 0. And it doesn't matter what f double prime is at that point, because we're interested in where the product of these two is smaller than or equal to 0. So if either one of them is equal to 0, then that x also works. So we're going to include that negative 3, 4. Okay, cool. Is there another place where we have green and pink? No, we just have green and purple. So we are done with case number 1. Right? Case number 2, we're looking for where the gradient is negative. In other words, we're looking at gray, and f double prime is positive. So we are looking for purple. Okay, so let's see where that occurs. So that is over here, right? We have gray and purple. This is where the gradient is negative and the graph is concave up. And then it stops over here, because at this point, the gradient stops being negative, it becomes positive, right? So then your graph is now concave up and your gradient is positive. And if you times those values together, you're going to get a positive number, which is not what we're interested in. So we're going to union that with starting at 1,33 recurring, or more accurately, negative 4 over 3, right? And then it stops at 0,7. Okay, and then again, are we including the bounds or not? So at this point over here, when x is equal to negative 4 over 3, we know that f double prime is equal to 0. And that's another one that we're interested in, where f double prime is 0 and f prime can be anything, because again, if f double prime is 0 and this is whatever it is, the result of this is just going to be 0, which is okay. We're looking for places where the product is smaller than or equal to 0. So we are definitely going to include negative 4 over 3. And for the same reason, similar reason, we're going to include 0,7, because at that point, f prime is equal to 0, which makes this expression equal to 0 as well. Right. So that concludes case number 2, the case where we have a negative gradient and a concave up graph. right? And then we also saw the cases for our turning points, right, where negative 3, 4 is included because the gradient is 0, 0, 7 is included because the gradient is 0 there, and negative 1, 3, 3, 3, 3, 3, 3, 3 is included because at that point f double prime is 0. It's a point of inflection. Okay, so that is our final answer then. Yeah, drawing up these tables was an interesting exercise that kind of did nothing for us. So yeah, I just recommend using the graph. I think it's more, at least it's more visible to me what's going on by looking at the graph. Okay, so I'm just going to quickly look at the memo and see if we're in agreement. So just heading right back to the beginning, I should have probably looked question by question. I keep forgetting. Right, negative 10 for our y-intercept, yes. Second question was a show question. We managed to show by substituting x is equal to 2, so that worked out. And then our factorization is x minus 2 times x plus 5 times x plus 1, and that is what we got. And then our graph, yes, we are in agreement about what that looks like. Then the interesting questions, right? So they get x is between negative 3, 4 and 0, 7. Yep, correct. The next one, we get x is equal to negative 4 over 3. Yep. And then the last one, which was very interesting, x is an element from negative 8 up until and including negative 3, 4, or the range from negative 4 over 3 up until 0, 7, both included. Yes, we did it.